You know, there's something fascinating when you look up on a clear night. Thousands of stars shining there, each one potentially surrounded by planets. And you wonder, are we alone? It's a question as old as humanity itself. But now, for the first time in history, we have the tools to actually try to answer it. When we talk about searching for life beyond Earth, we first need to agree on something basic. What exactly is life? Because if we don't know what we're looking for, we could miss it entirely. Here on our planet, all the life we know is made of carbon. It needs liquid water, it functions within certain temperature ranges, but even here, we found organisms living in absolutely extreme places. In volcanic vents at the ocean floor where water boils, in lakes so acidic they'd melt metal, even several kilometers underground, inside solid rock. So you think, well, maybe life is much more resilient and adaptable than we thought. That's why when scientists establish criteria for searching for life, they start with the basics: liquid water, a constant energy source, and certain fundamental chemical elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. But here's the interesting thing. These are just starting points, right? Because if there's something out there that works completely differently with a different chemistry, we could be looking right at it without recognizing it. The methods we use to search have evolved enormously. We can't physically travel to every distant world, at least not yet. So what do? We read their light. It's brilliant, actually. When light from a star passes through a planet's atmosphere, certain wavelengths are absorbed by specific molecules. It's like a chemical fingerprint. We can detect oxygen, methane, water vapor, things that could indicate something's alive down there. These are what we call biosignatures, the fingerprints of life scattered across the cosmos. And this is where astrobiology comes in. It's not just astronomy, it's not just biology or chemistry, it's all these disciplines working together, asking how life could begin, how it survives, how it might spread across the galaxy. We run computer simulations. We study the chemistry of early Earth. We send probes to the icy moons of our own solar system, Europa, Enceladus. They have oceans beneath their frozen surfaces, deep, dark oceans that have been isolated for billions of years. And those oceans could harbor life. Not life as we see it on the surface of Earth, but something adapted to eternal darkness, to pressure, to cold. Something that challenges our very definition of what's possible. Space missions are crucial in all this. The Mars rovers, for example, aren't simply picking up rocks. They're looking for patterns in those rocks. Minerals that form only in the presence of water, traces of ancient organic compounds, chemical signatures that whisper stories of a wetter, warmer Mars billions of years ago. We've sent orbiters to study atmospheres, landers to analyze soil, helicopters to fly through Martian skies. Each mission adds another piece to the puzzle. What's remarkable is we're living in an age where our instruments can detect these subtle clues from light years away. Just a few decades ago, the idea of analyzing another planet's atmosphere would have sounded like science fiction. Now, with space telescopes tuned to infrared and visible light, we're beginning to see these worlds in incredible detail. We're not just finding dots of light anymore. We're finding worlds with weather, with seasons, with chemical compositions. We can actually measure and analyze. It's not definitive proof yet, but it's the real first step toward answering one of the oldest questions we've ever asked. And I think that's what's important. We're not just searching for life, we're redefining what life could be. Every time we find a microbe in some extreme, impossible place here on Earth, it's like the universe is whispering to us, you're still not thinking big enough. And maybe the answer is already out there, written in light across the sky, just waiting for us to learn how to read it, waiting for us to build the right instruments, ask the right questions, look in the right places. Now, when you start talking about exoplanets, it's almost hard to believe how fast this field has exploded. Not long ago, we didn't even know if planets existed beyond our solar system. And now we've cataloged thousands. Thousands of worlds, each one unique, each one with its own story to tell. The first ones we found in the 90s were nothing like Earth. Massive giants, scorching worlds, orbiting so close to their stars that a year there would last just days. Hot Jupiters, we call them. Worlds where the temperature is so high that iron vaporizes and rains back down as molten droplets. But over time, with better telescopes and smarter techniques, we started finding smaller, cooler worlds. The kind of places that really could be habitable. Rocky planets, super Earths, worlds that might have solid surfaces, atmospheres we can study, conditions that could just possibly support life as we understand it. This is where the concept of the habitable zone comes in. It's the region around a star where temperature would allow liquid water to exist on a planet's surface. Not ice, not steam, but liquid water. The substance that, as far as we know, is absolutely essential for life. Too close to the star and the water evaporates. The planet becomes a Venus-like hellscape with surface temperatures hot enough to melt lead. Too far and it freezes solid. The planet becomes an ice world, frozen and lifeless. But even this is a simplification because a planet's atmosphere can change everything. A planet's atmosphere, for instance, can trap heat and extend that zone. A thick, insulating atmosphere could keep a world warm far beyond the traditional habitable zone. Carbon dioxide, methane, other greenhouse gases, they can create a blanket that holds in heat. A thin atmosphere could leave it frozen even if it's technically in the right place. Mars is a perfect example. It sits right on the edge of our sun's habitable zone, but its thin atmosphere means surface water can't exist in liquid form. It either freezes or sublimates directly into vapor. And the stars themselves matter just as much. A small, dim red dwarf has a habitable zone so close that its planets could be tidally locked. One side facing the star in eternal daylight, baked by constant radiation. The other in perpetual night, frozen in darkness. That creates all sorts of challenges for habitability, though it doesn't necessarily make it impossible. Some models show that with the right atmosphere, heat could circulate and keep the whole planet temperate. Wind patterns could transfer warmth from the day side to the night side. It's not ideal, but it's not necessarily impossible either. Larger, hotter stars have wider habitable zones, but they burn through their fuel faster. Maybe too fast for complex life to ever evolve. They might only shine for a few 100 million years before expanding into red giants. That's not a lot of time. It took life on Earth nearly 4 billion years to go from simple cells to complex organisms. So maybe the best places to look are around stars like our Sunday, mid-sized, stable, burning steadily for billions of years. We've even started getting examples of planets that look, at least from a distance, like promising candidates. Kepler, 186 farads, for instance, is roughly Earth-sized and sits in its star's habitable zone. TRAPPIST-1 has 7 planets, several in that coveted region. Proxima Centauri b orbits the nearest star to our sun and might, just might, have conditions suitable for life. And now with the James Webb Space Telescope, we can begin probing their atmospheres, searching for those chemical hints that might suggest something's alive there. But habitability isn't just about distance from a star. It's about geology, chemistry, magnetic fields, whether the planet has plate tectonics to recycle nutrients. Plate tectonics on Earth have been crucial for maintaining a stable climate over billions of years. They recycle carbon, they create fresh crust, they drive the rock cycle that keeps our planet geologically active, or a magnetic field to protect its surface from harmful radiation. Earth's magnetic field shields us from the solar wind, from cosmic rays, from all the radiation that would otherwise strip away our atmosphere and sterilize the surface. Without those, even a planet in the perfect spot could be barren. It could be a dead rock, lifeless, despite being in the Goldilocks zone. Mars, again, is our cautionary tale. It once had a thick atmosphere, flowing water, maybe even conditions suitable for life. But it lost its magnetic field, and over billions of years, the solar wind stripped away most of its atmosphere. What was once a warm, wet world became the cold desert we see today. And then there's the question of moons. A large moon can help stabilize a planet's tilt, keeping its climate stable for millions of years. Earth's moon does this for us. Without it, our axis would wobble dramatically over time, causing wild climate swings that might make complex life impossible. That stability might be a key ingredient for life to develop and survive. Time to evolve, time to complexify, time to create ecosystems and biodiversity. So when astronomers talk about the search for Earth-like worlds, it's not just about finding another blue planet. It's about weighing dozens of factors, each one capable of tipping the balance between a lifeless rock and a thriving ecosystem. Star type, planet size, orbital distance, atmosphere, magnetic field, geological activity, the presence of a stabilizing moon. All of these things matter. All of them contribute to whether a world can support life. And every discovery, Every faint, flickering signal from a distant star adds a new possibility to the list. It's like slowly piecing together a cosmic map, one that might eventually lead us to a place where, under alien skies, something is looking back. Maybe wondering, just as we do, if they're alone in the universe. When we think about contact with other civilizations, the first thing that comes to mind is, how would we even know they're out there? The idea of listening for signals has been around for decades. Projects like SETI, the Search for Extraterrestrial Intelligence, have been patiently scanning the skies with radio telescopes, just in case somewhere someone is deliberately broadcasting, just in case there's a civilization out there saying, "Hello, we're here. Is anyone listening?" The reason we focus on radio waves is simple. They travel far, they can pass through dust clouds, and require relatively little energy to send across interstellar distances. If you want to send a message across the galaxy, radio is one of the most efficient ways to do it. But even so, the space between stars is vast, unimaginably vast, and any signal, no matter how strong when it's sent, will fade into background noise over light years. By the time it reaches us, it might be just a whisper against the roar of the cosmos. There's also the problem of deciding what counts as a signal. The universe is noisy, really noisy. Pulsars spinning and beaming radio waves like cosmic lighthouses, quasars blasting radiation across the spectrum, the hiss of cosmic microwave background radiation, the afterglow of the Big Bang itself. It's all there, all the time, creating a constant background din, and any artificial transmission would have to stand out against that chaos. We've developed algorithms to filter for patterns, repetitive pulses that come at regular intervals, narrow frequency bands that nature doesn't tend to produce on its own. Anything that looks too structured, too organized, too artificial to be natural, we're looking for order in the chaos, for intelligence in the noise. But even if we detected something that looked artificial, the challenge would be proving it, because a signal, once found, has to be confirmed and confirmed again from different places at different moments. Otherwise, it could just be a strange natural phenomenon we haven't seen before, a new type of pulsar, an unusual cosmic event, human-made interference. We need multiple independent confirmations before we can say with any confidence that we've found something real. And then there's the other side, sending messages ourselves. We've done it a few times, like the Arecibo message in 1974, a binary coded signal aimed at a star cluster about 25,000 light years away. It carried information about humanity, about our DNA, about our solar system, a cosmic message in a bottle. Or the Voyager Golden Records, which aren't really signals but artifacts, carrying sounds and images from Earth, slowly drifting through interstellar space. They won't reach another star system for tens of thousands of years, but they're out there, silent ambassadors from our world. The truth is, if we're sending things out, we have to accept we might never hear back. The timescales involved are enormous, staggering. A message to a system 100 light years away would take 100 years to arrive. And if someone responded instantly, immediately upon receiving it, we'd wait another 100 to get their answer. 200 years for a single exchange. That's longer than the United States has existed as a nation. It's longer than we've had radio technology. It requires a patience, a long-term thinking that challenges our very nature as short-lived beings. Some scientists argue that maybe the best way to search for extraterrestrial intelligence is to look for technosignatures, not deliberate messages, but signs of technology visible from far away, the inadvertent fingerprints of an advanced civilization. That could be unusual infrared emissions from a Dyson sphere, a megastructure built to capture a star's energy, or artificial pollutants in an atmosphere, chemicals that only industrial processes produce, or laser pulses aimed into space for communication or propulsion. The idea is that any sufficiently advanced civilization might leave a detectable footprint, even if they're not trying to communicate with us specifically. But all this leads to a bigger question, a more troubling question. If the galaxy is full of planets and potentially habitable worlds, why haven't we heard anything yet? Why is it so quiet? This is the Fermi paradox, named after physicist Enrico Fermi, who asked this simple, profound question over lunch one day: where is everybody? And it has many possible answers. Maybe intelligent life is rare. Maybe we're one of the first. Maybe the steps from chemistry to life from life to intelligence, from intelligence to technology, capable of interstellar communication. Maybe one or more of those steps is incredibly unlikely. A filter so narrow that most worlds never pass through it. Maybe civilizations don't last long enough to overlap in time. Maybe there have been thousands of civilizations in our galaxy, but they rise and fall, and we're just happening to live in a moment when none of them are broadcasting. Maybe they destroy themselves, or evolve beyond technology, or lose interest in reaching out to the cosmos. Or maybe they're deliberately staying silent. Maybe there's a reason, a good reason, to not advertise your presence. The dark forest hypothesis suggests that the galaxy might be filled with civilizations hiding from each other because the risk of contact is too great. Whoever reveals themselves first might be putting themselves in danger. It's unsettling to think we could be surrounded by countless worlds and still remain alone in our awareness. Still, we keep listening. Every new telescope, every upgraded receiver widens our reach. Every year, our technology gets better, more sensitive, more capable of finding that needle in the cosmic haystack. Somewhere in the static and the starlight, there could be a whisper waiting, a sign that across the void, someone else once looked up at their night sky and wondered if they were alone. In the end, the search for life beyond our world is as much about us as it is about them. Every planet found, every faint signal detected is a mirror held up to our own existence, reminding us that the universe is vast, mysterious, and still full of unanswered questions. Questions we're only now beginning to have the tools to answer. If we go back in time, long before any life emerged, Earth was a completely different place, unrecognizable, alien in ways that would shock anyone seeing it. There were no forests or blue oceans as we see them today, no green continents, no life singing in the trees or swimming in the seas. It was a young world still forming, still settling into its current configuration, with a dense atmosphere filled with gases like methane, ammonia, water vapor, and carbon dioxide. Gases that would be toxic to us now, but gases that were essential for what was about to happen. The sky probably had a different color, maybe more reddish or orange, filter through all that methane and haze. And the surface was a mosaic of primitive oceans, incandescent rocks still glowing with internal heat, and active volcanoes constantly releasing gases and minerals into the air. It was a violent place, a place of extremes. But it was also a place where chemistry could run wild, where molecules could experiment, where the impossible could become possible. This primitive atmosphere was crucial because there was no free oxygen as we have now, no ozone layer to block ultraviolet radiation. And this means chemical reactions could occur much more freely without everything oxidizing quickly, rusting away before it had a chance to become complex. The oceans, or rather the chemical soups of these primordial seas, contained a vast variety of elements and compounds brought both from Earth's interior through volcanic activity and from impacts of asteroids and comets delivering ingredients from across the solar system. These impacts, by the way, weren't rare. It was practically constant bombardment. The late heavy bombardment, we call it. For hundreds of millions of years, Earth was being pelted by asteroids and comets. And each one brought heat, energy, and possibly organic molecules formed elsewhere in the solar system. Complex carbon compounds created in the coldest space, delivered to Earth's surface like packages from the cosmos. Energy was everywhere. Lightning flashed through the atmosphere, providing electrical energy for chemical reactions. Volcanoes released heat and minerals, creating hydrothermal systems both on land and underwater. The sun's ultraviolet radiation hit the surface without barriers, since the ozone layer didn't exist yet, providing another source of energy to drive chemical reactions. This combination of rich chemistry and varied energy sources created the perfect setting for simple molecules to start coming together and forming more complex structures. Another factor, and perhaps one of the most important, is that Earth was cooling but still had a lot of internal heat. This created different zones with varied temperatures and chemical conditions. In cooler regions, molecules could stabilize, could persist long enough to interact with other molecules. In warmer regions, they were forced to react, to transform, to break apart, and recombine in new ways. This contrast, this alternation between hot and cold, wet and dry, may have been fundamental for chemistry to transform into biochemistry at some point. The shallow oceans, for example, were probably true natural laboratories. Water evaporated under the sun's heat, concentrating salts and organic compounds in tide pools and shallow lagoons. Then rain returned everything, diluting and mixing and restarting processes. The tides caused by the moon, which was already in orbit, but much closer than it is now, also helped create cycles of drying and hydration. And these cycles, repeated millions of times over millions of years, might have helped molecules organize in increasingly stable ways, selecting for molecules that could survive these cycles, that could persist and eventually replicate. And we can't forget the hydrothermal vents at the ocean floor. These structures that release heated mineral-rich water could have provided refuges for stable chemical reactions, protected from the intense radiation of the surface. Down in the darkness, in the pressure where hot mineral-laden water meets cold ocean water, complex chemistry can happen. There, compounds dissolved in hot mineralized water could have accumulated and interacted, taking advantage of temperature and chemical gradients to create new molecular form, creating tiny chemical engines that could harvest energy from the environment. So when we think about the origin of life, the first step is to imagine this primitive Earth, an active, dynamic planet in constant transformation, a world of fire and water, of lightning and chemistry, of impacts and volcanism, a world that, even without life, was already unconsciously preparing the stage for the emergence of something completely new, something that would change everything, something capable of growing, replicating, evolving, and somehow beginning to tell its own story. Abiogenesis is perhaps one of the most fascinating and challenging questions in science. The central idea is that life emerged from non-living matter, that somewhere, somehow, on the early Earth, simple molecules began organizing into increasingly complex systems, eventually giving rise to something we'd recognize as alive, something capable of replicating, of evolving, of responding to its environment. The most famous experiment that attempted to simulate this process was the Miller-Urey experiment in the 50s. Stanley Miller and Harold Urey recreated in a laboratory an atmosphere they thought was similar to that of primitive Earth. They added water to simulate oceans, applied electric discharges to simulate lightning, and waited to see what would happen. And after just a few days, they found amino acids, the fundamental building blocks of proteins. This was a milestone, a breakthrough, because it showed that essential molecules for life can form naturally, spontaneously, under conditions similar to those of a young planet. You don't need magic. You don't need divine intervention. You just need the right chemistry and the right energy. But of course, forming amino acids isn't the same as forming life. Not even close. The next step is to imagine how these molecules began interacting, joining together, and creating longer chains. How amino acids link up to form proteins, how other molecules form nucleic acids, how lipids organize into membranes. One hypothesis is that clays or minerals on the surface served as scaffolds, as templates for organic molecules to attach and link to each other. These minerals might have helped catalyze chemical reactions, bringing molecules together and holding them in place long enough to bond, increasing molecular complexity one step at a time. Another well-studied possibility is that everything began in the ocean depths, at hydrothermal vents. In these environments rich in minerals and with temperature gradients, simple molecules could have accumulated in microscopic cavities, tiny pores in the rocks, protected from radiation and rapid destruction. There, chemical reactions would have occurred continuously, using the chemical energy released by the interaction between seawater and hot rocks. It's as if each microcavity were a small natural laboratory, a chemical factory producing increasingly complex molecules. But perhaps the most intriguing point is the question of self-replicating molecules. For life to begin, it wasn't enough to have complex molecules floating around. There needed to be something that could copy itself, that could make more of itself, because that's what life does. It replicates. It makes copies. RNA, for example, is a molecule capable of storing information like DNA does, but it can also act as a catalyst under certain conditions, helping chemical reactions occur. This dual nature makes it a prime candidate for one of the first molecules of life. This led to the RNA world hypothesis, a scenario in which, even before DNA and proteins, before the complex machinery of modern cells, there existed a simpler system, a set of RNA molecules that could copy themselves and compete for resources, slowly evolving toward more sophisticated system. RNA molecules that could store information, could catalyze reactions, could do many of the jobs that in modern cells are split between DNA and proteins. It's an elegant idea, a stepping stone between chemistry and biology. Over time, these structures could have enclosed themselves in simple membranes, forming protocells. These bubbles, made of lipids, would protect the internal molecules and keep chemical reactions happening in an isolated space, creating a barrier between inside and outside. This would have been a crucial step, because by isolating internal processes, by creating an inside and an outside, these first almost cells could become more efficient and more adaptable to the environment. They could control their internal chemistry. They could respond to external conditions. They could, in a primitive way, live. Still, each step in this process is a puzzle, a mystery we're still working to solve. We know it's possible because we're here, but we don't know exactly how it happened. We don't know which steps came first, which paths were taken, which of many possible routes led from chemistry to life. And that's what keeps the research alive, what drives scientists to keep experimenting, keep simulating, keep trying to recreate in the laboratory the most likely scenarios, testing each hypothesis, reproducing the conditions of early Earth, and seeing if at some point we can witness, almost as witnesses to history, the birth of the first spark of life. Panspermia is an idea that completely changes the way we think about the origin of life. It's a game changer. Instead of imagining that everything started here on this specific planet, on Earth and only Earth, it proposes that the ingredients, or even primitive forms of life itself, may have come from outside, from space, traveling through the cosmos until they found our world. And in a way, this greatly expands the scenario, because it means that life, or at least the potential for it, could be scattered throughout the cosmos, not tied to one world, but a cosmic phenomenon seeded across the galaxy. There are different versions of this hypothesis, different flavors of the idea. Lithopanspermia, for example, suggests that impacts on planets or moons that already have life could launch fragments of rock into space. A large enough asteroid impact could blast material into orbit, into space, carrying with it any microorganisms living in that rock. And some of these fragments, protecting microorganisms deep inside where they're shielded from radiation and vacuum, could travel for millions of years before landing on another world, delivering life like a cosmic seed. It seems unlikely, almost absurdly unlikely, but tests have shown that certain bacteria can survive extreme conditions, including vacuum and radiation. Bacteria like Deinococcus radiodurans can survive doses of radiation that would kill almost anything else. And if they were inside a piece of isolated rock, insulated from the worst of space's hazards, the chance of resistance, of survival, would increase even more. It's not impossible, just incredibly improbable. But in a galaxy with hundreds of billions of stars, improbable events can happen many times. Radiopanspermia is a different concept. It imagines that lightweight and resilient microscopic spores could be carried by the pressure of starlight itself, by radiation pressure, slowly navigating through interstellar space until finding a hospitable planet. It's a harder idea to prove because cosmic radiation is intense and could destroy these structures during the journey. The voyage between stars takes millions of years, even at the speeds radiation pressure could provide. Still, experiments with organisms like Deinococcus radiodurans show that life can endure much more than we had imagined. Maybe not millions of years in space, but who knows? Maybe with the right protective mechanisms, the right biochemistry, it's possible. There's also directed panspermia, which is more speculative, more in the realm of science fiction, but not entirely dismissible. In this case, life wouldn't have arrived on Earth by chance, by random accident, but intentionally sent by an advanced civilization. Maybe as a way to seed distant worlds, to spread life across the galaxy, to ensure that intelligence and consciousness persist, even if individual civilizations fall. It's something that enters the realm of astrobiology and also philosophy, because it raises profound questions. What if we ourselves are the result of an ancient experiment conducted by beings we'll never know? What if Earth is a terrarium, a garden planted by cosmic gardeners? From a scientific point of view, some evidence fuels curiosity, keeps the idea alive. Meteorites like ALH 84001, found in Antarctica and confirmed to have originated from Mars, contain structures and organic compounds that for some researchers could be remnants of ancient Martian life. Tiny structures that look, to some eyes, like fossilized bacteria. The debate continues. Most scientists think they're not biological, But the possibility hasn't been entirely ruled out. Other meteorites have brought amino acids and simple sugars formed in space, in molecular clouds and on asteroid surfaces, which shows that organic chemistry is much more common in the universe than we previously thought. The building blocks of life aren't rare. They're everywhere. What panspermia doesn't resolve, of course, is the initial step. The fundamental question, even if life came from elsewhere, from Mars or from another star system, it had to start somewhere, at some point. And that brings us back to abiogenesis, to the origin of life, from non-life, just displaced to another world, another time. Still, this hypothesis has a special charm, a poetic quality, because it transforms life into something that's not exclusive to Earth. Not a unique miracle that happened only here, but part of a cosmic network of exchanges and journeys that can last billions of years. A web of life spanning the galaxy. And to imagine that perhaps we're all space travelers from the beginning, that our ancestors, the first cells that gave rise to all life on Earth, might have fallen from the sky, completely changes the sense of our own history. It makes us citizens of the cosmos in the most literal sense. And it means that when we look up at the stars, we might be looking at our true home, the place our deepest ancestors came from before Earth was even habitable. The moon. It's always been there, hasn't it? Hanging in the sky, a constant companion, a silent witness to Earth's entire history. Long before any human being could imagine what it was, what it meant, it was there. Pulling at our oceans, lighting our nights, inspiring our myths and our poetry. It's curious because for centuries, for thousands of years, the question of how it came to be didn't have a clear answer. Just stories, myths, explanations that mixed imagination and observation and hope. In the past, there was the idea that it might have formed alongside Earth, that they were siblings born together from the same cloud of gas and dust that formed our solar system, as if they were two worlds that were born side by side, growing at the same time, coalescing from the same material. But the more we study, the more we analyze moon rocks brought back by astronauts, the more we realize this doesn't seem to make sense, because its composition isn't exactly the same as ours. There are similarities, striking similarities, but also differences that don't fit the co-formation model. There was also the theory that the moon might have been captured by Earth's gravity, that it formed elsewhere in the solar system and was wandering through space until it passed too close to Earth and got stuck, trapped in an eternal gravitational dance. It's interesting, even romantic, to imagine that. A celestial body traveling through the solar system, a wanderer, encountering Earth and getting caught, becoming our permanent companion. But then the evidence, the orbital mechanics, began showing that this capture would have been extremely unlikely, almost impossible. Because the orbits, the energy involved, the velocities required, nothing matched what one would expect from such an event. Capture is incredibly difficult. It requires very specific conditions that just don't seem to have existed. And there was still the idea that perhaps the moon had broken away from Earth itself, that it was once part of our planet, as if a gigantic piece of our world had been thrown into space, torn away by rotation or some other force, spinning until forming this satellite we see today. Moreover, at one point, it was imagined that the Pacific Ocean would be the hole, the scar, left by this separation. But of course, this hypothesis was dismissed because the measurements, the data, the geology simply didn't confirm it. The Pacific isn't a wound, it's a normal ocean basin formed by plate tectonics. And it's fascinating to think that for a long time we were in the dark about this, fumbling for answers. Even with telescopes, even with increasingly precise measurements of the moon's orbit and composition, even with centuries of observation, only with space missions, only when we actually went there and brought samples back, did we begin to better understand its chemical composition, its history, its origin. When they analyzed the material brought by the Apollo missions, when they looked at actual moon rocks in laboratories on Earth, they found that the moon and Earth share some very specific isotopic signatures, ratios of different isotopes that are like fingerprints, which suggested that somehow they had a common origin, that they were made from the same material. But at the same time, there were differences that couldn't be ignored, like the absence of certain volatile elements on the moon, elements that should be there if it formed the same way Earth did. indicating that it must have formed under extremely hot conditions, hot enough to boil away lighter elements. So the question of origin isn't just an astronomical curiosity, isn't just about satisfying our curiosity. It's linked to the history of the solar system itself, to understanding the violent early days when planets were still forming. Because understanding where the moon came from helps us also understand Earth's first millions of years. A chaotic period with impacts, collisions, violent changes that shape both worlds into what they are today. And of course, the moon isn't just a beautiful object in the sky, isn't just something pretty to look at. It influences the planet in profound ways, ways that might have been crucial for life. Without it, Earth's rotation axis could oscillate much more dramatically over time, wobbling chaotically. The tides would be different, much weaker, which might have affected how life evolved from the oceans to the land. Maybe even the evolution of life itself would have taken another path, would have been slower or never happened at all. Therefore, unraveling how the moon arose isn't just a technical detail, isn't just about solving a puzzle. It's like trying to read the first chapter of a story that to this day is still being written, a story in which the moon plays a starring role. The giant impact hypothesis is today the most accepted explanation for the moon's origin, and it's almost cinematic in the scale of what it describes, in the violence and grandeur of the event. Imagine primitive Earth about 4.5 billion years ago. The solar system is still young, still settling down. Earth is still hot, still forming, still being bombarded by debris left over from the formation of the planets. Its surface is partially molten, glowing red in places, with an atmosphere of vaporized rock and superheated gases. And then another body, a Mars-sized protoplanet that we call Theia, after the Greek Titan, who was mother of the moon goddess Selene, colliding with it. It wasn't a light bump. It wasn't a glancing blow. It was a catastrophic collision, an impact so violent, so energetic, that it vaporized part of Earth's mantle and launched an immense amount of debris into space. Imagine the energy, the force, more energy than all the nuclear weapons on Earth could produce, more energy than anything we can really comprehend. This debris spread out in orbit around Earth, forming a disk of incandescent material, of vaporized rock and molten droplets, circling our wounded planet. And over time, over thousands or millions of years, through gravitational attraction, they coalesced, they came together, fusing and cooling until they turned into the moon we see today. The beauty of this theory, its elegance, is that it explains various things that were previously difficult to understand. For example, the fact that the moon has a composition very similar to Earth's mantle in terms of oxygen isotopes and other elements, because much of the lunar material would have come from Earth itself, blown off in the impact, and at the same time, it explains why the moon has less iron and fewer heavy elements than Earth does, because Theia's iron core would have sunk through Earth's mantle and merged with Earth's core during the impact, leaving the moon formed mainly from lighter mantle material from both bodies. But it's not that simple. It's never that simple in science. When scientists began running computer simulations to test the hypothesis, to model the impact and see what happens, they realized that for the moon's composition to be so similar to Earth's, Theia would also have to have had a very similar composition to Earth, which isn't guaranteed and actually seems somewhat unlikely. Why would two different planets have nearly identical compositions? This led to variations of the original hypothesis, like the idea that the collision was even more violent, so intense and energetic, that it completely mixed and homogenized the materials of the two bodies, creating a disk of vaporized material that was thoroughly mixed before the moon condensed and formed. There are also debates, ongoing discussions about the angle and speed of the impact. The specifics matter. A more direct and fast strike, a head-on collision, could launch more material away from Earth entirely, sending it flying off into space, never to return, but might not keep as much of it trapped in Earth's orbit where it could form a moon. A more tangential impact, a glancing blow, could create just the right amount of debris with just the right velocities to form a large and stable satellite. Each simulation, each model, brings a slightly different scenario, different outcomes, and that keeps the discussion alive, keeps scientists refining the hypothesis. Some more recent studies even suggest that the impact may not have formed a debris disk that slowly came together over time, but that the moon could have formed almost immediately, rapidly, as a single body from a massive cloud of molten and vaporized material called a synestia. A synestia is this bizarre structure, neither quite a planet nor quite a disk, that can form after mega impacts. It's a donut-shaped cloud of vaporized rock spinning rapidly. This model, called the synestia moon, is still new and needs more evidence, more testing, but it's an interesting variation that could explain some things the traditional model struggles with. And of course, the mystery of Theia still exists. It haunts us in a way. We'll never find Theia, not as a separate body. Not exactly. It's gone, destroyed in that ancient collision. But perhaps in a way, it never disappeared. A part of it would be in Earth's core, iron from Theia's core that sank down and merged with our own. And another part would be in the moon itself, Theia's mantle material mixed with Earth's orbiting above us, looking down at us every night. This idea that our satellite is at the same time a part of us and a part of another lost world gives all of this an almost poetic dimension, a beauty amid the violence. Even being essentially the result of a colossal destruction event, the moon is also a creation, a birth from catastrophe. Recent discoveries about the moon have changed a lot the way we see our satellite, have transformed it from a dead rock into something much more interesting. For a long time, there was this idea, this assumption, that the moon was a completely dead, inert place, geologically dead, with nothing interesting happening for billions of years, just sitting there, cratered and cold, unchanged since the ancient bombardment ended. But little by little, space missions and more precise instruments began showing that it's not quite like that. The moon has surprises. For example, the detection of water ice in polar regions, especially in permanently shadowed craters that never receive sunlight, was a milestone, a game changer. These craters act like cold traps, cosmic freezers, and the water there, delivered by comet impacts over billions of years, may have been preserved for unimaginable spans of time. This isn't just a scientific curiosity. It's not just interesting for its own sake. It's also a vital resource for future human missions. Because this water can be used for drinking, yes, but also to generate oxygen for breathing and even to manufacture rocket fuel. Hydrogen and oxygen. Water is rocket fuel if you can split it apart. It makes the moon a potential staging ground for deeper space exploration. Another important discovery came from more detailed analyses of lunar samples and from new collections made by missions like China's Chang program, which has been returning fresh samples from parts of the moon we'd never visited before. These analyses show that the moon may still have some level of geological activity, even if very discrete, very subtle. There are signs that its interior still retains enough heat to cause small moonquakes, lunar earthquakes, and that's fascinating because it challenges the view of a totally dead body. The moon is cooling, yes, but it's not completely cold yet. These moonquakes may be linked to the gradual contraction of the moon as it cools slowly over billions of years, and its surface adjusts, cracking and shifting. As the interior cools, it shrinks slightly, and the crust has to accommodate that shrinkage, creating faults and cliffs called scarps. And there's more. Recent measurements of the lunar soil composition revealed minerals that we hadn't previously identified there, or hadn't recognized as being present in significant quantities. Some of these minerals form only under conditions of extreme impact, which tells us more about the history of collisions that the moon has suffered, about the violence it's endured. Each crater, each layer of regolith, of lunar soil, is like a page in a geological book, a record of impacts and volcanic eruptions and space weathering. And reading those pages is like going back in time to periods when Earth itself was undergoing drastic transformations, when life here was just beginning or hadn't started at all. Furthermore, there's the issue of gases that from time to time seem to escape from the lunar surface, outgassing events. Some detectors have already registered small releases of gases like radon and argon, and this may indicate that there are internal processes that we still don't fully understand, pockets of gas trapped in the interior that occasionally find their way to the surface. It's nothing comparable to Earth's active volcanism, to our explosive eruptions and lava flows, of course. But it serves as a reminder that the moon still holds secrets still has stories to tell us. High-resolution images captured by probes like the Lunar Reconnaissance Orbiter, which has been photographing the moon in incredible detail for years, also revealed very recent surface formations, geologically speaking. Roughness, landslides, and marks of smaller impacts that occurred in the last tens of millions of years, which in planetary terms is almost yesterday, practically the present. This reinforces the idea that the moon is in constant transformation, even if at a much slower pace than Earth, even if you'd have to watch for millions of years to see significant changes. It's not frozen in time, it's aging, evolving, changing. And perhaps one of the most interesting implications of all these discoveries is realizing that the moon is at the same time a historical archive and a natural laboratory. It preserves traces of the solar system's past in a way that Earth cannot. Because here, the climate, erosion, and plate tectonics erase almost everything. Earth is geologically active, constantly recycling its surface, but the moon isn't. Its surface is ancient, preserving a record going back billions of years. Looking at the moon through this new lens is like rediscovering an old neighbor and realizing that he always had stories he never told, secrets he kept, waiting for us to develop the technology to listen. When we talk about the geometry of the universe, we're actually trying to answer a question that seems simple, but requires looking at everything, absolutely everything, simultaneously. It's like trying to see the shape of something that has no edges, that has no outside, we can go to and observe from a distance. We're inside the thing we're trying to measure. Imagine being an ant on a balloon, trying to determine if the balloon's surface is flat, curved, or something else, without ever being able to step off the balloon and look at it from outside. That's our situation. Einstein's general relativity already tells us that matter and energy shape space-time, that they're not separate things. They dictate how space curves, how it bends and warps. So cosmic geometry is precisely that. The global shape, the overall structure of all space. And here comes a fundamental concept that everything hinges on, the energy density of the universe. Because it's not enough to talk just about stars, planets, galaxies, the visible stuff. There's visible matter, yes, but also dark matter, which we can't see but can detect through its gravitational effects. There's radiation, light, and other electromagnetic waves filling space. And there's dark energy, this mysterious force that seems to be accelerating the universe's expansion. All of this contributes to the total energy density. All of it matters. If this density is exactly a certain critical value, a specific number that cosmologists have calculated, the universe is flat in the geometric sense. Euclidean geometry applies on cosmic scales. Parallel lines remain parallel forever. The sum of the angles of a triangle is exactly 180 degrees. The kind of geometry we learned in school. But if the density is greater than this critical value, if there's more stuff in the universe than this threshold, the geometry closes in on itself like the surface of a sphere. It's positively curved. In this universe, parallel lines would eventually meet. The angles of a triangle would sum to more than 180 degrees. And if the density is less than the critical value, the universe opens up like a saddle, like a Pringle chip, expanding forever with negative curvature. Parallel lines diverge. Triangle angles sum to less than 180. But how do you measure this when you cannot step outside and look from the exterior? When you're trapped inside the very thing you're trying to measure, we use signals that come from the past, from billions of years ago, messages written in light. The cosmic microwave background radiation, for example, is a snapshot of the universe when it was just 380,000 years old, when it first became transparent to light. Before that moment, the universe was so hot and dense that light couldn't travel freely. It was opaque, like being inside a fog. But at 380,000 years, it cooled enough for atoms to form, for light to break free, and that light has been traveling through space ever since, carrying information about the universe's shape. The small variations in this radiation, those tiny hot and cold spots in the cosmic microwave background, carry information about the curvature of space. If the light from these fluctuations reaches us a little more spread out or more concentrated than expected, if the spots appear larger or smaller than they should in a flat universe, it indicates whether space is flat, open, or closed. It's like looking at a pattern on a curved surface versus a flat one. The pattern gets distorted in predictable ways. We also look at gravitational lensing, the bending of light around massive objects. When light from distant galaxies is bent by massive objects in its path, by clusters of galaxies or even individual galaxies, the amount of distortion, the degree of bending, depends on the curvature of the space it passes through. In a flat universe, the bending follows certain rules. In a curved universe, different rules. By studying many examples of gravitational lensing, we can infer the overall geometry. And there's also the mapping of the distribution of galaxies, the large-scale structure of the cosmos. Surveys, like the Sloan Digital Sky Survey, have mapped millions of galaxies, showing how matter is arranged on gigantic scales in filaments and voids in a cosmic web. And this distribution also tells us about geometry. The patterns we see depend on how space is curved. The curious thing, the remarkable thing, is that as far as we can measure, everything points to a universe very, very close to flat. Our best measurements suggest the universe's curvature is within a few percent of zero, maybe exactly zero within our measurement uncertainties. But this almost is intriguing because it could be exactly flat, which would require a very precise initial condition, an incredible fine-tuning, or it could be slightly curved and we still don't have sufficient resolution to perceive it. Our measurements have error bars. There's uncertainty. Any deviation, even tiny, even just a fraction of a percent, changes what the final fate of the cosmos will be. Whether it will expand forever, slow down, but never stop, or one day collapse back on itself in a big crunch. So when we talk about the geometry of the universe, it's not just an aesthetic question, not just mathematicians playing with abstractions. It's about the past, the present, and the future of everything that exists. It's about our ultimate destiny. And at the same time, it's about us trying from within, like those ants on the balloon, to guess the shape of the infinite container in which we live. What existed before the Big Bang? It's strange, isn't it? Trying to talk about what came before the beginning. It feels paradoxical. It's like asking what's north of the North Pole. Once you're at the North Pole, there is no north. Every direction is south. The thing is, time itself, time and space, they're not things that existed before the Big Bang. At least not in the way we understand them. Not in any way we can meaningfully talk about. According to what we know, according to our best current understanding, the Big Bang wasn't an explosion in space. Wasn't something that happened somewhere. It was the beginning of space itself, of time itself, of everything. The origin of the universe. So when we ask what came before, we're asking a question that maybe doesn't make sense, that might not have an answer, not in the usual way, not in any way our language can capture. The equations, the models, Einstein's equations of general relativity, they take us back in time, back toward the beginning, back to that moment, that first moment. But when you get to the very beginning, when you approach t equals 0, things get fuzzy. The math breaks down. General relativity, as beautiful and successful as it is, stops working. It tells us that everything, all matter, all energy, all space, all time, was compressed into a singularity, a point of infinite density and infinite curvature. But infinity is a red flag in physics. It's a warning sign. It means the theory isn't working anymore, that we've pushed it beyond its limits. Something's missing, something more fundamental that we don't understand yet. So that moment, t equals 0, we can't see past it with our current physics. Not yet. And maybe we never will with the tools we have. Maybe it's not like a curtain we can just pull back to reveal what's behind. It's a boundary, a limit, possibly a fundamental one. Time might have started there. That's the weird part, the mind-bending part. We think of time as always flowing, right? As éternel, always ticking forward, second by second, past a future. But if time began at the Big Bang, then there wasn't a before, there wasn't a ticking clock, no past to move through, just nothing, or maybe not even that. Because nothing implies the absence of something, and there wasn't even absence before time existed. It's hard to think about, nearly impossible. Our brains, our intuitions, they're built to deal with beginnings and ends, with causes and effects, with time always flowing. But the universe doesn't always care about what makes sense to us, about what our monkey brains can easily grasp. And in this case, asking what existed before time itself is like trying to remember what you were doing before you were born. There's no reference, no framework, The question itself might be meaningless, but still, we try. We imagine. We wonder. Because even if time started there, even if that's the beginning of everything we can measure and know, we still want to ask what lies beyond, what could have caused it, where it came from. We want to know if that boundary, if it's real or just a veil, something that hides a deeper truth, a layer of reality we haven't uncovered yet. And that's what makes this question so haunting, so compelling. It's not just about the start of the universe. It's about the nature of existence itself, about causation, about whether anything can truly begin or whether everything must come from something else in an infinite regress, about whether time is a property of our universe alone or something more fundamental, something that could exist without stars, without galaxies, without matter or energy, without anything, just time, or maybe not even that. So we're left there at the edge of everything we can know, peering back into something we might never fully grasp, the place where space and time came into being, the beginning of beginnings, and beyond it, silence. Not darkness, not void, not emptiness, just something we don't have words for, something we might never fully understand, a mystery that might remain forever beyond our reach. So if we try to push past that edge, that boundary where time begins, we have to start thinking differently. Not just differently in terms of theory, but fundamentally different in ways that challenge everything we think we know about cause and effect, about before and after. Because there are some ideas, some serious scientific proposals that suggest maybe the Big Bang wasn't the beginning. Not really. Maybe it was just a moment, a transition, a phase change in something larger, and what came before, well, that could be just as real as everything that followed. There's this idea, this hypothesis that cosmologists have explored, that maybe the universe cycles, that it expands like it's doing now, but then one day, perhaps trillions of years from now, it contracts, it shrinks back down, and then instead of collapsing into a singularity and ending, it bounces. It rebounds in another Big Bang. A new universe born from the death of the old one. Some call it the cyclic model, or the oscillating universe. It's not universally accepted. There are problems with it, but it's being explored seriously by physicists. And if that's the case, if this model has any truth to it, then the Big Bang wouldn't be the origin of everything. It would be one of many beginnings, perhaps even infinite beginnings stretching back forever. A heartbeat of the cosmos, expanding, collapsing, rebounding, repeating endlessly like a cosmic breathing. Each cycle might last hundreds of billions of years, so long that entire civilizations could rise and fall in what's just one breath of the universe. And then there's the multiverse. That one's complicated, controversial even among physicists. It suggests that what we call the universe, everything we can see and measure, is just one bubble, one patch in a vast, maybe infinite ocean of universes. Each bubble a different universe, with potentially different laws of physics, different values for fundamental constants, different particles, maybe even different dimensions. And in that picture, our Big Bang was just the formation of our bubble, our pocket of reality. Nothing special, really. Just one of countless others, each with its own beginning, its own history, its own fate. Some physicists, working from theories like eternal inflation, think these bubbles are constantly forming, constantly budding off from some greater, deeper substrate of reality. Imagine a pot of boiling water with bubbles constantly forming and rising. Each bubble is a universe. The water itself is this underlying quantum field, the sea of potentiality from which universes emerge. In this view, Big Bangs are happening all the time, everywhere, in this larger meta-reality. We just happen to live in one particular bubble, asking questions about our particular beginning. There are also ideas from quantum mechanics from the bizarre world of the very small that might apply to the very beginning, like the notion of a quantum vacuum, which isn't empty at all, despite the name. It's not nothing. It's seething, bubbling with energy, with virtual particles popping in and out of existence, borrowing energy from the vacuum for brief instants before disappearing again. Some theories say that from this sea of quantum uncertainty, from this foam of possibilities, entire universes can emerge spontaneously, randomly, without cause in the traditional sense. Just fluctuations that happen to grow instead of disappearing. And if that's true, then what came before our Big Bang might have been a kind of quantum foam. a state where time and space as we understand them didn't exist, where only probabilities and potentials existed. No time, no space, no matter, just pure quantum possibility. And one fluctuation, just one among countless others, triggered our reality, inflated into our universe, created everything we know, just like that. No creator needed no first cause, in the traditional sense.